1.8 Higher Order Derivatives. Southwestern College, Professor Maria Olivas. Higher order derivatives. Objectives: find higher order derivatives. Solve applied problems involving higher order derivatives. 1. Higher order derivatives. Because the derivative of a function is itself a function, we can take derivatives of derivatives. Notation: given y equals f of x, the first derivative of f of x, or we can also write this as f prime of x, comma, y prime, comma, dy dx. For our second derivative notation, we can write this as the second derivative of f of x, or f double prime of x, comma, can also write y double prime, comma, or another way that we could write this is we could write d squared y over dx squared. Let me explain this a little bit more. When we take the derivative with respect to x of y, and then we choose to take the derivative of this function again, so it would be the derivative with respect to x of the derivative with respect to x of y. It's like we can multiply these derivative operators together. The d's will give me d squared, and the dx's will give me dx squared. So this represents the second derivative with respect to x of y, which can be written as d squared y over dx squared. I'm just going to go ahead and take the work that I just did here. I'm going to lasso it and I'm going to move it upward so it's not in the way, so that I can continue writing here down below. And similarly, for our third derivative, we can write the third derivative of f of x, or we can also write f triple prime of x, comma, which can also be written as y triple prime, comma, which can also be written as d cubed y over dx cubed. I'm going to go ahead and draw a big curly bracket on the right-hand side of my derivative notation that I just wrote down. On the right-hand side of the curly bracket, I'm going to write the nth derivative, and this is going to represent different ways that we can represent the nth derivative, or derivatives that are higher than the third derivative. We can write the nth derivative as the nth derivative of f of x, which looks like f, and then that f is going to have a superscript on it. We're going to open up a set of parentheses, we're going to write an n, and then we're going to close those parentheses for that superscript, and then we're going to write our x within parentheses on the right hand side. We can also write this as the nth derivative of y, also similarly with the y and then a superscript on the y on the right hand side. We're going to open up a set of parentheses for that superscript, write the n, and then we're going to close the parentheses on that superscript. Or the nth derivative of y with respect to x, which would be d, and it looks like d is being raised to the nth power with the n inside a set of parentheses, y all over dx, and then we have the superscript on the x, and once again that superscript is open up a set of parentheses, our n, and then close our parentheses. And these are all different ways we can represent the nth derivative of our function. Example 1. Given f of x equals 9x squared minus 8x plus 5, find a f prime of x. So f prime of x here is going to be equal to 18x minus 8. And we're going to box that answer in. B, the second derivative of f of x. f double prime of x is going to be equal to 18, and we're going to box that in. C, the third derivative of f of x. F triple prime of x is going to be equal to 0. Example 2. Given f of x equals 4x raised to the 5th power plus 5 over x, and then minus the square root of x. Find a f prime of x, or the first derivative of f of x. The first step is going to be to rewrite the function. Whenever you have variables in the denominator or variables inside of a radical, we're going to want to rewrite it so that all of our variables appear to be in the numerator, and we're going to use either negative exponents to achieve this, or we're going to use fractional exponents to rewrite anything that's using radical notation. In this case, f of x is going to be equal to 4x raised to the 5th power plus 5x raised to the negative 1 power minus x raised to the 1/2 power. If we take the derivative of this function, we're going to get, for the first derivative of f of x, f prime of x is going to be equal to 4 times 5 times x raised to the 5 minus 1 power minus 1 times 5 times x raised to the negative 1 minus 1 power minus 1/2 x raised to the 1/2 minus 2/2 power. If we simplify this function, we will get f prime of x equals 20x raised to the 4th power minus 5 times x raised to the negative 2 power minus 1/2 x raised to the negative 1/2 power. And we're going to box this answer in. For b, we're going to find the second derivative of f of x. We're going to use our boxed in function to get this derivative. So looking at our first derivative of f of x, we're going to get that f double prime of x equals 4 times 20 times x raised to the 4 minus 1 power minus 5 times negative 2 times x raised to the negative 2 minus 1 power minus 1/2 times negative 1/2 times x raised to the negative 1/2 minus 2/2 power. The second derivative of f of x, it's going to simplify to this. F double prime of x is going to be equal to 80 x raised to the 3rd power plus 10 times x raised to the negative 3 power plus 1/4 times x raised to the negative 3/2 power. And we're going to box this answer in. C, the third derivative of f of x. So f triple prime of x is going to be equal to 3 times 80 times x raised to the 3 minus 1 power minus 3 times 10 times x raised to the negative 3 minus 1 power minus 3/2 times 1/4 times x raised to the negative 3/2 power minus 2/2. If we simplify this function, we will get f triple prime of x equals 240x squared minus 30x raised to the negative 4 power minus 3/8 x raised to the negative 5/2 power. And we're going to box this answer in. Two, applications. Position, velocity, and acceleration. Suppose you were given a function s of t that describes the position of a particle at time t. Then velocity equals rate at which position changes with respect to time. Average velocity. For average velocity, I'm going to begin by writing down the formula for slope. M equals y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. The 2 points that we're going to use to substitute into the slope formula are going to be these 2 ordered pairs, a comma s of a, which I'm going to label with an x sub 1 and y sub 1. And then we're going to have b comma s of b, which I'm going to label with x sub 2 and y sub 2. In the first ordered pair, a is going to represent x sub 1, and s of a is going to represent y sub 1. In my second ordered pair, b is going to represent x sub 2, and s of b is going to represent y sub 2. We're going to now substitute into the formula for slope. So average velocity is going to be equal to s of b minus s of a all over b minus a. I'm going to go ahead and draw a cloud around this, and this is going to have an arrow pointing towards the right, and I'm going to write down that this represents the slope of the secant line. Instantaneous velocity. I'm going to underline the word instantaneous because whenever you hear this word, you should be automatically thinking about a derivative. I'm going to point an arrow downwards from the word instantaneous, and right below the word instantaneous, I'm going to write down the word derivative. So instantaneous velocity is going to be equal to v of t, which is also equal to s prime of t, or the first derivative of our position function. So our instantaneous velocity is going to represent the derivative of the position function. Acceleration. I'm going to underline the word acceleration, and I'm going to draw an arrow pointing downwards below it. And downwards below it, I'm going to write down that acceleration is the derivative of the velocity function. So acceleration is going to be equal to a of t, which equals v prime of t, or the first derivative of v of t, which is equal to s double prime of t, or the second derivative of s of t. Example 3. An object is dropped from a height of 200 meters. The height of the object above the ground, measured in meters, is given by the equation s of t equals negative 4.9 t squared plus 200, where t is measured in seconds. A. Find the height of the object after 2 seconds. In order to find the height of the object after 2 seconds, we're going to go ahead and use our position function, which was given to us in the problem. S of t. We're going to substitute 2 for t. So I'm going to go ahead and underline the word height because that's what's letting me know that I need to use my position function. I'm going to write down my position function. S of t equals negative 4.9 times t raised to the second power plus 200. Above the words 2 seconds, I'm going to write down t equals 2. And this is what I'm going to substitute for t. So s of 2 is equal to negative 4.9 times 2 squared plus 200. So s of 2 equals negative 4.9 times 4 plus 200. So s of 2 is going to be equal to 180.4 meters. Now, in order to write out our answer, I'm going to write out a little sentence explaining what our answer represents, and I'm going to make sure to write in our units. The height of the object after 2 seconds of being dropped is 180.4 meters. And I'm going to go ahead and box that answer in. B. Find the average velocity of the object from t equals 0 to t equals 2 seconds. In order to find average velocity, I'm going to need 2 ordered pairs. My 2 ordered pairs are going to be 0, s of 0, and 2, s of 2. For my first ordered pair, 0, s of 0, I'm going to draw an arrow to the right from that ordered pair, and I'm going to write this ordered pair as 0, 200. So 0, 200, I would come up with this y coordinate if I were to substitute 0 into my position function. So s of 0 is equal to negative 4.9 times 0 squared plus 200, which will just be equal to 200. For my second ordered pair, 2, s of 2, I'm going to go ahead and draw an arrow pointing to the right of that ordered pair, and I'm going to write down this ordered pair as 2, 180.4, and I got this value for this y coordinate in part A when it asked for the height of the object after 2 seconds of being dropped. I'm going to go ahead and label my ordered pairs here as x sub 1, y sub 1 for my first ordered pair, 0, 200, and I'm going to label my second ordered pair 2, 180.4 as x sub 2, y sub 2. And I'm going to be substituting into my slope formula m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So I'm going to go ahead and I'm going to begin by writing s of 2 minus s of 0 all divided by 2 minus 0. This is going to be equal to 180.4 minus 200 divided by 2 minus 0, which is equal to negative 19.6 divided by 2. This will simplify, and this will be equal to negative 9.8 meters per second. And we're going to go ahead and box that answer in. This is going to represent the average velocity of the object from t equals 0 to t equals 2 seconds. C. Find the instantaneous velocity of the object at time t equals 2 seconds. In order to find the instantaneous velocity, we need to find the derivative, the first derivative of our position function. So let's begin by writing out our position function once again. S of t equals negative 4.9 t squared plus 200. If we find the first derivative of s of t, we're going to get s prime of t equals v of t, which is going to be equal to negative 9.8 t. Now we're going to substitute t equals 2 in order to find the instantaneous velocity at 2 seconds. So v of 2 will be equal to negative 9.8 times 2, which is equal to negative 19.6 meters per second. And we're going to go ahead and box this answer in. D. Find the acceleration of the object at time t equals 2 seconds. In order to find acceleration, we're going to need to find the first derivative of our velocity function. We just found the velocity function in part C, so I'm going to go ahead and rewrite that here. So s prime of t, which is equal to negative 9.8t, and remember s prime of t is our velocity function. We are going to get our second derivative from our first derivative of s of t. So s double prime of t is going to be equal to v prime of t, which is equal to a of t, which equals negative 9.8. So a of 2 is going to be equal to negative 9.8. And our units for acceleration are going to be meters per second squared. This represents a rate of change of our velocity function. We're going to go ahead and box our answer in.